My name is Mark Daniel. I work at Infineon in Bristol, working in the tri-core CPU verification team. So my presentation is talking about how we have improved our regression times by a factor of 10. And so regressions are something that all of us have to deal with in life as verification engineers, whether that's running test cases or specimen regressions or various types of different regression we might be running. Most of us have to deal with them. Nobody really likes having to run them because they take too long, take too many resources, and we all have to debug the failures that they generate. Over the last 13 years, I've been working at Infineon here in Bristol and have developed a number of different regression scripts and working on various IP projects and CPU verification projects. At the end of last year on the tri-core project, we took a step back and looked at where we were wasting most of our time in running our regressions, and we came up with some interesting ideas for speeding up our regressions. So that's basically what this presentation is going to look at, is how we have sped up our regressions by 10 times. So let me look at the next slide. Okay, so basically we have 45,000 tests in a library, and this is our original regression flow. So I'm going to explain it so that you can see where we made the improvements. So the test library has 45,000 test cases. So a test case is contains some assembly files for the processor and some test bench control files and some metadata. These test cases are organized into test suites, and these test suites are then run as a regression. So that helps the terminology. So our test library it lives in a version controlled directory structure. So for each test case, there's a directory. I mean, each test in each directory has each of the files for the test case. We add tests to this library every day using our test generator, and at the end of each day, we have to label this library to enable it to be run a regression on a defined set of tests. So that currently lives in the clear case, and that takes. So if we look at the bottom of the chart of the slide, we have some timescales on how long each of these steps takes. So the purple triangle at the bottom here, this bit, reflects how long it takes to label those 45,000 tests in clear case, which 3 hours is quite a long time to take to do a label. Okay, so once we have our labeled, or once we have our library, to run a regression, we need to create a run area, or this is how we used to run it. And this involved copying all the tests for a test suite. In this case, we're talking 20,000 tests, and we had to create a directory structure. And the time this took was almost an hour. It could take longer, depending on the load on the system. And yeah, so that took an hour. Then from that run area, we had to find the list of tests that now existed there. From there, we created a test list. This find took another half an hour. And so before we could even start running our regression, we'd spent an hour and a half maybe, to finding out which tests we actually needed to run on this at this particular point in time. So once we had our test list here, we can we would submit these via LSF individually. So each test would be submitted as a separate LSF job. LSF is our load sharing farm facility. I'm not sure quite what LSF stands for, but that's the tool name. And then each test runs within the test run area, and it basically runs the test and leaves its files behind for parsing later. One issue we had was that the maximum number of tests that we could run in parallel on our cluster was 300, and this was limited by the disk access, but we'll talk about that later. The yellow triangle here at the bottom represents how long it took to submit all of the tests, or 20,000 tests, to the cluster. And so yeah, it took 1 second per test, which was almost 5 hours. So hence the reason we haven't finished submitting our regression until 6 or 7 hours after we'd started off. And then the execution, because we were limited to 300 in parallel, would take us up to 10 hours on a good day. Okay, so that explains our regression flow. And then at the end, once all our 20,000 tests had run, we could generate a report, and we find that generate a report of how well the regression had run, which is ultimately what we're looking for. Okay, so we identified 3 areas for improvement to our flow. First was the test library, and the next was the network storage, and then finally it was the speed of submission of our jobs to the cluster. So I'm going to talk about each of those separately and in a bit more detail. So the main issue with our test library as it existed was that the clear case labeling was very slow. We've already talked about that. And one thing that we found is that our test library was too big for clear case to store. We actually broke the clear case fob structure, and which unfortunately is not able to be fixed. Okay, so how are we going to solve this problem? We looked at various solutions. We looked at various other version control systems, but they all suffered from similar issues, whereas the capacity was not necessarily there, and it still required network storage to store all these things. So, our solution was to create a MySQL database to store all our test cases. This was a slightly big change for a hardware engineer to start thinking about creating databases to store tests. Some of the engineers, when I proposed this, some of the engineers were asking, well, where will my test files be? Which directory? Where can I find my tests? And there was another worry that we couldn't support version control in a database. You'll find that we have come up with solutions for all of these queries, and I'll go through each of those in step. So we developed an interface script for the users so they could get their test and add new tests to the database. They can list tests, and they can find tests. And also they can check out tests and edit them and modify them and put them back into the database as a new version. One of the things that a database enables is a much faster searching for tests, and searching for different parameters that exist. So we can, that it also speeds up the test list creation, which was one of our slow processes. It took us an hour and a half in your system, but now that can be done in a couple of seconds. So also test case files are also stored in the database, which it's taking us beyond just metadata. It's the whole test case and the whole assembler file and all the associated files that go with that. So, like I said, we needed to implement some version control and labeling within the database, and that's what our database schema that we developed allowed us to do. We could label instantly, and we could also check out and check in at test level and create versions of tests and then see them and go back to those if we needed to at any point. So that covers our test library. The next thing that we needed to work on was or identified as an issue, was our network storage. So the trend has always been towards, to solve regression times, is to throw more CPUs at the problem. And then so the problem with that is becomes a bottleneck writing back to a network disk somewhere, and we found that there was a ceiling where if we were running more than 300 jobs in parallel, all writing back to a single network filer, the filer's performance degraded so much so that we may as well have been running 10 jobs in parallel. Okay, so what were the main issues? It was slow to create those large directory trees on the filer. It's slow to write them when we're executing tests. And then I've just talked about the ceiling of 300 parallel jobs, and then we also need to clean up that directory structure at some time after we've run, and that takes time as well. So our solution was to move to local disk. So every machine has a disk on it storing its operating system, but there's also a lot more space available, so we could use that. So what are the advantages of this? Well, there's no need for generating those large directory trees on the network filer. And when the test is actually running on a machine, so this is running the simulator or building the test, and we're actually saving we found we were saving 20 seconds of I/O time per test. So our average test time was 100 seconds. So we instantly saved 20% of our execution time purely by moving to a local disk. So once the test is, the disadvantage of it executing locally, we don't have any files left over at the end, so we had to record the result of our test into a database, and that's storing that into a new results database, and then we remove the run directory, so there's no log files left over. And of course, the best advantage that we get from this is that we can run more than 300 jobs in parallel. We can run 1,000 if we had that many CPUs, but that was one thing. Okay, covers most of it. The next thing that we needed to do was to speed up our submission of jobs. This is the part that was taking 5 hours in the past, so that was the 1 second per test. And by submitting tests individually, we were putting a heavier load onto the scheduling system within the load sharing facility. So we moved to, there's a concept within most load sharing tools which allows you to submit job arrays. And so this is what we did. We used job arrays, and what this allows was instant submission of however many tests you are trying to run. So you can run, whether you're submitting 10 tests or 10,000 tests or 20,000 tests, it takes the same amount of time, a couple of seconds. And once they're submitted, the load sharing tool can handle those jobs much better. It can schedule them faster onto all the execution hosts, and it can make a much more efficient job of it. And of course, it's easier to gather statistics on the performance of a regression. So to have a look at our new regression system, let's have a look at the new flow. So here we have our test database. Looking at the timescale along the bottom, we originally had regressions that were taking us from time 0 to 10 hours to run, which was basically an overnight regression. So we now moved to the test database, which allows us to get a test list instantly, which means there's no time taken. We can submit those jobs to LSF again instantly, and then they can so there's no time on our timescale for submission. And once the test is running, the test is pulled out of the database. It's very quick. It then runs the tests on the local disk, and then we record the result into another SQL database. Over here is our results database. And then once a regression started, our reporting tool here can instantly give feedback on how the regression is progressing. So you can see failures and passes as soon as you get any results back. So that covers what we did and what we now have. So this is basically where my claim at the beginning on the headline of this presentation, that we're getting 10 times faster regressions. We now run time for 20,000 test regressions, gone from 10 hours down to 1 hour or less. Okay, so to summarise, not sure how I'm doing on time. We now have much faster regressions, which is an obvious statement. We have three sizes of regressions that we used to run here. Infineon, Tricor, we had a mini regression or a coffee break regression of 200 tests, and that used to take 20 minutes in the old system. It now takes 2 minutes in the new system. So this means you have no time to drink coffee anymore. We have MIDI regression. Now this gives us a much better quality check on changes that engineers are making to design or verification code. And this MIDI regression of 1,200 tests used to take 80 minutes or an hour and a half. And now we've reduced that to 10 minutes. So this means this is now the new coffee break regression. And another thing that we can do, the good advantage is that the example I've been working through all the time is the full regression of 20,000 tests. This was up at 10 hours, and we've now reduced that to less than an hour. I've actually seen it run through in 40 minutes. So this means that we can now turn around a full regression or full verification of our Tricor in less than an hour. It means we can turn around multiple regressions a day, and we can handle multiple releases each day. So it also means that users can check more configurations rapidly by having regressions that run 10 times faster. And in summary, we've done all this with free tools, without any new hardware, or the need for any new EDA software. And yeah, that's it from me.
Any questions from the audience on this? I have one question, Mark, if you can hear me, which is just a quick one. If these regressions run a lot more quickly, do you push a lot more of the responsibility for running regressions back to designers on check-in? Does it change the way designers do their check-in?
Yeah, we find that because designers can run that MIDI regression in 10 minutes, they're actually able to find bugs in their new code before it gets handed over to verification, which is always a good thing. It's better to find out that something's broken before you check it in than to find that you've broken the whole overnight regression. So yeah, it's a good thing.
And as a consequence, are you finding less bugs in the design that gets checked in? The designers finding the bugs earlier?
I thought I said that, but yeah, I agree. There's less bugs in the code that we get delivered from design because they are able to run much more testing up front.
Okay, thanks, Mark. We're going to give you a virtual round of applause now.